Alright students, welcome back. If you're watching this, we are having another snow day, but we need to keep moving with these phase diagrams. So I'm going to make this available on YouTube. Remember last time we talked about the idea of phases versus microconstituents. And the whole idea is phases are what phases are in equilibrium. Microconstituents are how are the phases distributed. And that's what controls the microstructure or the properties. So we're going to look at, just to remind you, let's go to the lead tin phase diagram that we were looking at. Remember, we were saying if we're at a point like this, you could always draw a tie line and do the lever rule and figure out what phases are present and what their composition is. But if we're looking at the microconstituents, the idea is cool down slowly from high temperature. And we said if we're at this point over here on the left, the microstructure would look like proeutectic alpha. That's alpha that was around ahead of time. Remember we did the lever rule calculation right above, and it was half liquid and half alpha above. There's alpha. Here's liquid. That's above the line. But below the line, we said that all of the liquid that was around is at exactly 61.9 once we get to this temperature of 183 degrees C, and when we cool down it turns into a eutectic mixture. So we said we've got microconstituents here, microconstituents would be proeutectic alpha and eutectic mix. All right. So looking at our example over here, if I cool this down, the microstructure looks like proeutectic alpha and eutectic mix. If I'm right at the eutectic point, it's just going to look like a eutectic mix. That was like a mixture of alpha and beta like this. And if we were anywhere over on here, we said the microstructure would be proeutectic beta and mix. Okay? So pro beta, and this is our eutectic mix plus eutectic mix. So to go back to our discussion here, phases versus microconstituents, in all cases moving across this region at these 3 points we just looked at, we could call this point 1, point 2, point 3. At all 3 points we still have alpha and beta phase, but the microconstituents are different and the microstructure looks much different. All right? So that's kind of what we reviewed last time. Now, let's go forward a little bit and let's talk about this idea of other uses of the phase diagram. Well, we talked about this last time, but one thing we could do is use it to sort of work backwards. That's work the problem that we've been doing in reverse. We have been, in the past, we have known, so let's go back to that phase diagram we just had. I'll draw it over here. In the past, we've known what the composition of the alloy is. Let's say it's right here. We called that C0. And then we talked about, well, what would the microstructure look like there? Well, now we're talking about working it backwards, which is, what if we know what the microstructure looks like? What if we know what the microstructure looks like? How could we figure out what the composition is? So going back to this, that is, if the microstructure looked like this, let's just say we looked at the microstructure and it had this much proeutectic alpha, and then the rest is our mix. Well, then we could go to the phase diagram and say, well, where would we have to be? Well, right here, where I drew this line before, that would be about 50-50. Proeutectic alpha and eutectic mix. But now the microstructure that I've drawn over to the left, if you look at it, maybe we have only about 20% proeutectic alpha and the rest eutectic mixture. Well, that's going to put us somewhere over on this side, right? Because we have more eutectic mix, which means we'd be closer to this liquid side. So we'd be somewhere over here. So now we've got sort of, we could figure out where we are for some unknown composition. All right. So again, we're talking about working the problem backwards, which is not, do we know the composition of the alloy, predict what's there? We measure what's there. Where do we have to be on the phase diagram in terms of composition? So let's take a look on another phase diagram here, a similar problem. So we're going to do an example problem. And the problem is let's say that the temperature, so here's an example problem. The temperature is 250 degrees C, and I measure that the amount of alpha, the weight fraction of alpha, is half, and the weight fraction of liquid is a half. And so the question is, what is the composition of this alloy? Again, we're working the problem backwards now. So we know that we're at 250 degrees C, so that's right here. Let me write that over on the left, 250 degrees C. So we're somewhere in the alpha plus liquid region, which puts us here, somewhere in here. But if we've measured that there's half and half alpha and liquid, that would put us right here at this composition where my triangle is, because right, I'd have to have half alpha over here and half liquid. That would be midway in between. So what's the composition of this alloy approximately? Well, let's extend this down here. And we say, oh, it's about 23%. So C0 of the alloy would be 23 weight percent 10. Now, the reason I worked that problem is because you have a homework problem much like it. All right? Again, that's sort of working the problem backwards. Okay. Now, let's continue on and let's keep talking about our iron-carbon system. Iron-carbon phase diagram. That's where we left off the other day. Remember, we said the phases of importance are austenite, which is the FCC form of iron, ferrite, which is the BCC form of iron, but that's just a little sliver right there, and Fe3C, which we said is a line phase over here on the right side of this phase diagram. Now, let's take a look and talk about some terminology. Now, remember, we already talked about different invariant reactions. We said this is a eutectic point up here at 4.3 weight percent carbon. That's where we said the region of cast irons because it's easier to melt up there. There's a paratectic point up here. Paratectic. Remember, that's where a liquid plus a liquid plus a solid delta goes to a new phase, gamma phase. This eutectic over here was liquid upon cooling goes to gamma plus Fe3C. That's that phase over here on the right, Fe3C. But there's another invariant point on this phase diagram that is very important, and that's right here at 0.76. This is probably the most important point on this phase diagram. Okay, so this is a eutectoid point, and that's where gamma, a solid, when we cool down, and gamma is at 0.76 weight percent carbon. When we cool down, it splits into two phases. Alpha, which has hardly any carbon, it has 0.022 weight percent carbon, plus Fe3C, which has a lot of carbon, 6.7 weight percent carbon. Now that eutectoid is really an important point on this phase diagram, so much so that we label steels on the left side of this hypoeutectic, and on the right side of this hypereutectoid. Sorry, this should be eutectoid on the other side because it came from a solid. Now those steels are going to be much different because on one side, over here on the left, you're going to have a different microstructure than over on the right. Now there's something very important that happens at that 0.76, and I'm going to go to some pictures of your book. We're going to skip some slides here to talk about what happens at that point. But basically it's a solid that splits into two solid phases. So I'm going to skip ahead to a figure, and that's this figure right here. And basically what it shows is this is how this eutectoid mixture of alpha and Fe3C formed from austenite. So here's austenite over here, and we have a mixture of alpha and Fe3C in layers that forms on the right. But we know for this to form, carbon has got to diffuse from areas that are going to become alpha over to the areas that are going to become Fe3C because they have a lot of carbon. So this forms a layered structure Kind of like what we saw before with a eutectic mixture, except this is a eutectoid mixture, and this is called, this microstructure in steel, this mixture has a name, a special name for steel. So a eutectoid mixture of alpha plus Fe3C is called perlite. That's just a name given to that micro constituent that's a mixture of alpha and Fe3C. Now, the historic reason for that perlite name is because the first people that started to polish and look at steels under the microscope saw that those steels kind of looked like mother of pearl when they looked at it with their naked eye. It was kind of iridescent, and that's because the layers of alpha and Fe3C scatter light in strange ways. So they called it, looked like pearl, so they just called it perlite. But what we know now is that it's this layered mixture of alpha, ferrite, and Fe3C. It's a two-phase mixture. So now let's go back to our iron-carbon phase diagram here, and let's talk about a steel that has, we're going to do an example problem here. But to work this example problem, I think what we're going to do is we're going to skip to the next page, because really we only need just this part of the phase diagram is what we're interested in for steels. So I'm going to kind of blow up that section of the phase diagram. So we're going to do an example, and we're going to figure out what phases are present in a 1040 steel that has 0.4 weight% carbon at low temp, down at like room temperature. Well, you can see that this phase diagram only goes down to 400 degrees C, but essentially what we have anywhere below this line, this eutectoid line temperature, 727, anything we have below there is pretty much what we're going to have down at room temperature. So 1040 steel, here's about 0.5, so 0.4 is right about here. So we're going to go up here and we're just going to draw a dot where we are somewhere below that line, and we're going to draw a tie line and do the lever rule. Okay. And so the phases present are alpha and Fe3C. It's labeled right here. The amount of alpha, or the composition of alpha, let's write that first. The composition of alpha is at about 0.02 weight% carbon. It hardly has any carbon. The composition of Fe3C, so that's right here at this dot on the left. The composition of Fe3C is this dot over here on the right that I just drew. That's its composition is 6.7 weight% carbon. So I have two phases present. One has hardly any carbon and one has a lot of carbon. Now, how much of each phase is present? So that's the weight fractions, or amounts, weight fractions. The weight fraction of alpha is just the opposite side, so here's alpha on that side, over the total. Well, you can see just by looking at this, there's going to be a lot more alpha than Fe3C. And if you plug in the numbers, the opposite side length is 6.7 minus 0.4 over 6.7 minus 0.02. If you go through and figure that out, you'll get that it's 94% alpha, which makes sense. I mean, look at how much more we have to have for alpha. And the weight fraction of Fe3C is 0.4 minus 0.02 over 6.7 minus 0.02, but it's just going to be 0.06, right? It's all got to add up to be 100. So that's the amount, that's the phases present at room temperature. But what we want to talk about is next is, what is the microstructure going to look like? Well, this is similar to what we saw with the lead tin phase diagram right at the beginning of this lecture. So I'm going to go to this next page and I'm going to draw this section of the phase diagram that we're interested in over here to Fe3C on this side, Fe3C, which is at 6.7 weight percent carbon, so it's weight percent carbon on the bottom. And then we've got this region over here. It's a very thin region. So this is really the region that we're interested in right here. So this is at 0.76 right there. And this composition right there was 0.02. That's the maximum amount of carbon I can dissolve in alpha. This is the alpha plus Fe3C region. Well, let's talk about what would the microstructures look like at various positions. Well, if it was right here at exactly 0.76, that's the eutectoid composition, and I cooled down, that steel would just look like a mixture of alpha and Fe3C. Eutectic mixture. Now, how would a steel look like right here if I was about midway in between? By the way, that's about a 1040 steel that we just looked at, and we'll look at it again in a second. What's it going to look like right here at 0.4? Well, I'm going to have above about half and half alpha. So I'm going to draw these alpha grains. So this is going to be called pro-eutectoid alpha ferrite. And then the rest is going to turn into perlite, because whatever austenite was left at the very end, that's gamma phase up here, it's at exactly 0.76. Right? If you draw tie lines as you go down, it's approaching 0.76. Now, what's the microstructure going to look like if I'm up here at like 1% carbon? That's a really high carbon steel. Well, instead of being pro-eutectic alpha, I'm on the right side over here where there's gamma plus Fe3C over here. So the phase that forms first now is Fe3C, so I get Fe3C. I'm going to draw it along the grain boundaries. I'm going to draw it like dark so you can know. So I'm going to call this as pro-eutectoid Fe3C, and then the rest is going to be the mixture once I cool down. Remember, the mixture is called perlite. Over here, sorry about that. Sorry, students. Okay, so this is called, over on the right, perlite over here. And what does the microstructure in the middle look like? It's all perlite. So let's calculate the micro constituents at a 1040 steel and relate it to the phases that we saw. So let's go to a new phase diagram here. So if we're at 1040, that's right about here. It's about halfway in between, 0.4. Remember, we do the lever rule calculation right above, gives us a hint of what's going to happen below. So right above the line, here, let's imagine what happens if we cool down slowly. So way up here, it's all austenite. I'm going to draw like solid grains, austenite. When I get down to right above this 727, that's right here, this line that I just drew across here, it's about half and half, but we're going to calculate. So it's alpha and gamma. Now how much of each? Well, let's do the calculation above the line. Alpha is the opposite side of the lever, that's 0.76 minus 0.4 over 0.76 minus 0.02. Well, if you figure that out, it turns out that you get 0.49, so it's about half, 0.49. And then how much is gamma above the line? Well, it's 0.4 minus 0.02, 0.76 minus 0.02. But it's 51. It's got to add up to be 100, right? Now, remember, what happens when we cool down below? Well, all of the austenite that was around is at 0.76. So it turns into perlite, so the microstructure below is proeutectoid alpha, proeutectoid alpha, and then the austenite gamma becomes perlite. About, and then look, let's go back to that. How much of each? Well, how much is proeutectoid alpha? Well, it was alpha that was around before I hit the eutectoid. That's 0.49 from above. How much is going to be perlite? 0.51. Now, one last variation on these diagrams is, what if I want to know, so let's ask this question, how much alpha is in the perlite? Well, let's take a look here. From before, so I'm going to page back a couple. From before, we figured out that the total amount of alpha, this is the total alpha that I'm circling, is 0.49. Sorry, 0.94. That's 94%. Back here, the amount of alpha in the proeutectoid alpha is 0.49. So how much alpha is in the perlite? That would be equal to the total alpha, 0.94, minus 0.49. Right? Because this is the total alpha, and this is the proeutectoid alpha. Again, both of these are correct, but the reason we go through this above and below and try to determine what the microstructure looks like, that's the one on the left there, is that's what we see in the microscope. We don't really see the amounts of phases, necessarily total alpha and total Fe3C. We just see big white patches here, big white patches, and then we see this gray layered stuff here. So this looks like white and this looks gray. So when we look through the microscope, let me show you what this actually looks like. It looks like this. This is the microstructure of a 1040 steel. Now it's hard to tell, but you can see that the perlite is sort of gray patches, but you can start to see that it's a mixture of alpha and Fe3C, and then you can see we've got this proeutectoid ferrite. Right? Remember, the 1040 steel was on this side of the eutectoid point, over on this side. Now, what if I was on the other side? Well, it would look like this. If I'm on the other side over here, I'm going to have proeutectoid cementite. In this case, it kind of looks like a lighter phase here when there's enough of it. That's this stuff right here. But we've got this proeutectoid cementite, or Fe3C, and then the rest is perlite. You can see there's a lot less proeutectoid Fe3C here in this microstructure compared to what we had a second ago, because the length of this lever is so long on this side. That is, it's almost all going to be perlite. It's almost all going to be perlite. All right. So, if you can work that, if you can understand this, what we just did here a second ago with figuring out the difference between total amounts of phases and microconstituents, you should be able to work any of these problems. Now, we're going to talk about one last concept of importance in this chapter, and it's related to your homework, and that is this concept of non-equilibrium cooling. Remember, equilibrium means that we cool and heat very, very slowly so that diffusion can occur and all of the phases can come to equilibrium. But if we start cooling rapidly, things change a little bit. So there's a nice discussion in your book that I wanted to go over, and it's related to this non-equilibrium cooling. We're going to look as an example a simple phase diagram, copper-nickel phase diagram. You may remember that was a binary isomorphous system that looked like this. Well, the idea is if I'm cooling very, very slowly, and I watch what happens as I cool down from liquid to solid, at each point, the phases can come to equilibrium, and the compositions of the phases sort of even out, so that at the end, this is the composition of the solid. But if I'm cooling really rapidly, take a look at those tie lines here. Let's say that I cool down to this tie line right here, it's 0.1. So I rapidly cool down to this temperature that I've labeled 1. You can see that there is going to be a little bit of solid alpha and mainly liquid. So if I drew a picture at 0.1, it would look like this. There's a little bit of solid floating in the liquid. But its composition of the solid is way up here. We could just give it a number. Maybe it's about 70 weight percent copper. Or sorry, nickel. So it's 70 weight percent nickel. But if I drop suddenly to temperature 2, do you all see that the composition of the next solid to be added is actually down here now at like 65. So now this composition of this solid in here was 70 weight percent nickel. And then I added a little solid on the outside, but its composition is given over here at temperature 2. It's about 65 weight percent nickel. And let's say I could immediately drop the temperature to temperature 3. Well, now you can see it changes again. Now it's about 60. So now I add some more solid on there. Same with these other ones. And that solid's 60 weight percent nickel. And then finally, right before I get to the end, this is maybe, I don't know, 55. So now I add some more solid on there, and it's 55. So what we've sort of shown there, oops, where's my, sorry, I lost our slide. So what we've shown there is that the microstructure doesn't end up being a uniform composition, or in other words, there's a phenomenon known as coring that happens, and that means the core of the grains that form of the solid have different composition than the outside. Now, there's a nice figure from your book that shows that. So coring means, and this happens if we cool down rapidly. If we cool down really, really slowly, diffusion can occur so that copper and nickel can diffuse, you know, from the center to the outside and vice versa, and so that all the composition can even out. But if we cool fast, the composition doesn't have time to change as rapidly because it relies on diffusion, which is a time and temperature thing, so that we get a microstructure, let me fast forward to here, that looks like this. That is, the core of the grains have a different composition than the center. That's very important. What it means is, for casting, in the metals world, for casting, often it's not a very uniform composition. The first liquid that forms has a different composition than the last liquid that solidifies. Or sorry, the first solid that forms has a different composition than the last solid that solidifies. And that's kind of shown in this picture on the right here. So you can see the cores of these grains are different than the outside. All right. So that gets us through chapter 9, and you should be able to work all of the homework problems now. So get on it and let me know if you have any questions. The homework is due on Monday, so you got to start some of these phase diagram problems, but once you get into them, they should be fairly straightforward. They're all the same no matter how complicated the phase diagram gets.